To get an idea of how areas are affected under a change of variables, let's study a specific example. Let's see how areas are changed by the specific mapping phi of u and v equals u plus v plus 3, comma, 3u plus v plus 1. So I'd like you to think about this as mapping u and v to x and y. So this first one is going to represent an x-coordinate written as a function of u and v, and the second represents a y-coordinate as a function of u and v. Let's see where the unit square in the UV plane gets sent over in the XY plane. So the unit square in the UV plane has coordinates 0, 0, 1, 0, 1, 1, and 0, 1. And let's give those guys names. Let's call them P, Q, R, and S. And just one by one, let's figure out where each of these points is taken over in the XY plane. And I'll do that by substituting into phi. So first let's look at what phi of point P is. That'll be phi of 0, 0. If I plug in 0 for u and 0 for v, I'm going to get 3, 1. So the point 0, 0 gets mapped over to 3, 1 in the xy plane. I'm going to draw this a little bit larger. So this point is going to be phi of p. Next, let's do the same thing for q. That's phi of 1, 0. So I'm going to take this formula and substitute u equals 1 and v equals 0. So in the first component, that's 1 plus 0 plus 3, which is 4. And for the second one, it'll be 3 plus 0 plus 1, which is also 4. So phi of 1, 0 is 4, 4. Let's place that in the graph. So phi of q is there. Next, we can do R and S. This would be a great time for you to pause the video and see if you can get it on your own. I'll continue working. Phi of R is phi of 1, 1. I plug in 1 for u and 1 for v. That takes me to 6, 5. And finally, for phi of S, I have phi of the point 0, 1, which is 5 and 2. So plugging that in, I end up at this point. Now you might notice that both these functions are linear, so it shouldn't surprise you that these edges get taken to the edges between these points that we map to. So what you can see is that phi maps this unit square that would corresponding to our S over here to a parallelogram, which I could call R. So what I'd like to figure out is how does the area of the parallelogram compare to the area of the unit squared? Well, of course, the area of the unit square is 1. So let's spend a little bit of time figuring out the area of that parallelogram. Well, in the beginning of the semester, when we were studying vectors, we found out how to find the area of a parallelogram by taking a determinant. Remember, if you formed vectors for two adjacent edges of the parallelogram and took the determinant, then the absolute value of that determinant was equal to the area of the parallelogram. So let's see if we can figure out what this vector is and what that vector is. So this was the point 3, 1, and this the point 5, 2. So if I call this vector v for the moment, then the vector v I can get by taking the terminal point minus the initial point, which gives me 4, 1. And that's reasonable to get from here, 5 minus 3 is 2, 2, 1. That's reasonable because to get from here to here, I'm going 2 to the right and 1 up. Notice the same thing happens up here, which is what makes it a parallelogram. Q, phi of Q, was the point 4, 4. So if I call this vector W, then W I can get by taking the terminal point minus the initial point, which is 1, 3. So the area of that parallelogram is the absolute value of the determinant of 2, 1, 1, 3. Which is the absolute value, that's right, that's the absolute value of 6 minus 1, or 5. So the area over here is 5. While the area over here is 1. So under this mapping, areas are multiplied by a factor of 5. So let's draw some conclusions on this, or make some observations. The first one is that areas are multiplied by 5. What that's going to mean to us later is that dx dy is going to be 5 du dv. And another point is a little bit subtle, but notice that this is an orientation reversing map. Notice if I go P, Q, R, S, that's going counterclockwise around this square, whereas if I go phi of P, phi of Q, phi of R, phi of S, that goes clockwise around that rectangle. A way that that would show up in determinants is that if I take the vector from phi of P to phi of Q, that was 1, 3. And if I go from phi of P to phi of S, that was 2, 1. And notice that that determinant is 1 minus 6, or negative 5. So it turns out that if you take the determinant of this mapping, if you take the determinant of those two vectors going in the same order, we end up with a negative number, and that negative indicates that we have an orientation reversing map.